So now you are getting into now delve deeper. So why are we all doing this? Even when you talk about your let us say statistics, what are you trying to infer? You are trying to infer something about the population, that is like predict, estimate, whatever you want to call it, right, but about the population, right, but we only have the sample. So there should be a bridge or a connection that connects the sample to the population, right. And what do I mean by that? You have a set of sample parameters or sample metrics, let us say numbers like mean, median, mode, right, all of those. What do we call it as? Parameters, variables, or what is it? Estimation quantities, right, estimated quantities about something else, right, about the population. Now have we in statistics we only talk about sample, but is it anything worth to talk about the sample without knowing the truth? If I do not know the truth, can I talk anything about the sample? I got a sample, how do I know x bar is correct? This way of estimating mean, ideally what should be x bar? So let me ask you, so this is x bar, right, ideally let us ask me this, x bar should tend to what? X bar should tend to, let us say as n infinity, as n tends to infinity, x bar should tend to what? This is sample mean, right. Now ideally sample mean is an estimator of what? Is an estimator of population. You are trying to estimate the population quantity from the sample quantity. That is what inferential statistics is all about. The descriptive statistics, I stay there, I summarize, I am happy, I leave, but that is not what you want to do in a typical setting. You want to infer about the population. Why are we doing clinical trial? Is it to make sure it is working on a small subset of population? No, you are trying to prove that using this sample you want to prove what? You want to prove that it will work on a larger audience, larger population, right. So now your estimate from the sample, your population parameters or population quantities that you measure from the sample should be an estimate of the population. So now tell me why x bar is important, all the more important. X bar is the best predictor to minimize the mean square error, and it is the best predictor of both the population quantity, not about the sample itself, right. You are nothing to predict about the sample because you have collected the data, there is nothing to predict about the sample. X bar is a estimate of the, or when you want to use when you want to predict about a population, x bar is a best estimate in terms of mean square error, and median is a best estimate in terms of mean square error when you want to predict the population value, right. Let us be very clear. Now whatever we have learned, mean, median, simple quantities, what we have learned so far is only that of a sample, but unless I know about population I cannot compare both. You see what I am saying? I know something about the sample because I am collecting the data, I can summarize the data, I can plot the data, I can take mean, median, variance, standard deviation, etc., blah blah blah. I can develop n number of what? Theoretical quantities. Let us at this point call it as theoretical quantity, I mean sample quantities. I can do n number of derive or calculate n number of quantities from the sample data, but it has to have relevance with regard to population. So what is important? Should we not study about population at this juncture? Only when you know population, something about the population, then you can take a sample, derive metrics or quantities that will match that of the population. The sample quantity should match that of the population. So now we are going to delve deeper, and this is where the idea, when you talk about, we always talk about probability and statistics. Probability talks about what? In this context, probability is going to talk about population. No estimation, nothing. Probability is only about population. statistics is about sample. And if you want to think of it, today's case, so probability is like a lab under ideal conditions. When under ideal conditions, what will work, what will not work. Statistics is like implementation in the field. Okay. At the lab scale, what do you want to do? You want to make sure your algorithm performs the best. So that is what. So probability and statistics go together. Probability is about population, and you develop metrics or quantities that will match the population parameters, population quantities at certain conditions, ideal conditions or under assumptions. In reality, that assumptions may not be met, but at least I will know that under certain assumptions my sample statistic is equal to the population mean or population true parameters, true quantities. My sample statistic, the statistic developed out of the samples is equivalent to that of the population parameters under certain conditions. Only if you establish that, then it makes sense to use that sample statistics in reality. If you do not know anything about population, all the statistics you develop from the sample will not have any meaning. Why? You are not trying to infer anything about the sample. Sample is already given. You are only trying to infer about population, and therefore you need to know about the population. So probability is wholly concerned about talking about the population in our case. Okay. So that is when it will become theoretical. Why? Because you do not know the entire population. You are not measuring the entire population. So the population parameters will become theoretical. But this is very important because this is the lab setting. Okay. Only then you can connect your sample statistic to your population parameters. Clean? So you understand why do we learn probability? You are not learning probability because of chance, etc., blah blah blah. Okay. That is also not even correct to say that because you are talking about idealistic conditions. So probability is all about population. Understanding the dynamics of the entire population, the population parameters are the important quantities that will give information about the population. Okay. So the population mean will be very different from the sample mean. Population variance will also be different from the sample variance. Population will have a different skewness. Okay, we will talk about it, how the spread of the data is, left side or right side of the mean, etc. I can talk about how peak the data is, kurtosis. I can even talk about the relationship in the data, all of that at the population level, and I will develop equivalent sample statistics that will match the population parameters at under ideal conditions. Once I establish this connection, then what can I do? I can do a clinical study. Let us say I can only worry about the sample and then say x bar, my sample mean anyway I know is a good estimate of population mean under certain conditions. Okay. Now under certain conditions we will know that. So if you perform the experiments close to that under certain conditions, then you know x bar is a very good estimate of population mean. So if x bar is significantly greater than or less than whatever you expect, then what are you expect? What are you trying to infer? Your population, it will be happening in the same case with regard to population. Suppose in 100,000 people you have taken a sample size of 100,000 and you proved it that by vaccine there is an certain amount of antibodies developed. Let us call it as x bar. Some x bar antibodies have developed, and x bar is a good estimate of population mean under large numbers. When you do large number of samples, here your sample size is not small, right? 100 million, 100,000. Then you can say, look, in 100,000 my x bar is very high compared to 0. What is the ground condition? You do not develop any antibodies at all. That is 0. You have developed a very good amount of antibodies. X bar is very high. That means it is going to work in the population as a whole as well. This is the fundamental idea. Now to do all of that, you should show x bar is related with population mean, right. So that is what we are going to learn about probability. Let us be very clear, it is not theory, it is a purpose, it is done purposefully so that we connect stat and probability. Stat is about data, probability is about defining the useful parameters of the population itself that are of interest. Okay. So with that note, let's begin. So when you talk about probability, you are talking about not just an any experiment, you are talking about a random experiment. What is the definition of a random experiment? So what do you mean by random experiment? Outcome is not fixed under what? Outcome is not fixed is not a technically, can you be technically precise? What is a random experiment? The outcome of this experiment is uncertain even when conducted under what? Same conditions. Okay. So even when you conduct the experiment under same conditions like tossing a coin or throwing a die, I am conducting under same conditions, but my outcomes are not same. It need not be the same. So measuring a temperature is the same. To give you, what is an example for a deterministic experiment? What is the example of a deterministic experiment? Okay. F equals to ma. Is there anything uncertain about it? You understand? That is a deterministic experiment. Okay. That is a deterministic experiment. Whereas even a simple thing like measuring temperature is not deterministic. So in the world, real world, at least today, whatever you deal with is all what? Random experiments. Like your ECG will be constant. EEG, no. None of your biomedical signals are actually deterministic. Very simple, it is actually as random as it could be. Can you give any biomedical signal which is deterministic? Like an equation I can write and this is what will happen across the population. So that should tell you why random experiment is important. Whatever you measure from the body is a random experiment. What kind of measurement you take, it is actually a random experiment. Be it pulse oxygen, blood sugar levels or oxygen, none of them is deterministic. Okay. So all in all, today we will only focus on random experiments. Today most of the entire science focuses on random experiments. It is not an understatement, because deterministic people have been looking at it and then it has been done for quite a long, okay, but not at this level. Okay. So now when you talk about a random experiment, any outcome is a sample point, right? A sample point is the most basic outcome of a random experiment. Like you just measure a temperature at this moment, that is a sample point you have measured. And remember, what is the population then? What is the population of an experiment? What is the population of a random experiment? That is what we call it a sample space. Population are set of all outcomes, right? And what do we call it as an event? These are basic definitions. What do we call it as event? Any single occurrence. What is it? Event is not an experiment, right? What is an event? Something of interest to me. That is always the event, right? Something of interest to me is what is event is, right? So in a temperature I may be interested in an event where the temperature is between 35 to 40. That is an event. Anything between 35 to 40 I may be interested in. Or when you take in reality in a hospital setting or in a clear in a storage setting, anything above 0 degree is concerning when you are storing a vaccine. We all know -4 is ideal, right? I mean sub-zero, it depends on how you store. -4 is for milk, if I am not wrong, yeah, -4 is for milk, but depending upon the nature of the vaccine you may want to store at different temperatures. Now anything above a certain limit is an event that is of interest to me, right. So event is something, some outcome which is of interest to you, outcome or set of outcomes that is of interest to you, clear. So these are basic definitions of a, when you talk about populations. So I have given an example, sample space, you know what is the sample space, set of outcomes, a single point is a sample point and anything of interest is your event, okay. And usually you represent it using Venn diagrams. You are all familiar with Venn diagrams? Okay, good. And by definition what is, let us come to, I have not talked about the probability part, I have talked about events, subspaces. How do you define probability? How do you define probability? Chances of occurring an event, okay. But then how? With regard to what? Whole population. So mathematically how do we define? There are several ways of, at least 2 well known ways of defining a probability. We will take what is known,
the event occurrence by the sample space.
Okay. So we will go with what is known as a frequentist approach. Okay. So there was not a formal definition of probability until 1930s, I guess 1930s are even better. Like we take this frequentist approach where we talk about probability of an event. And of course with a catch, limit n tends to infinity. This is very important, okay. Limit n tends to infinity, n of a by n. Otherwise how do you define probability? When I say chance, yes, that is a good definition, chance, but what is chance? With regard to what? How do I measure probability? That is what we are defining as frequentist approach, but this is measurable. So look at what are the other ways in which people have defined probability. Probability is not new, probability is probably 300-400 years old. When did it start, any idea? Probability, where did it start? Gambling, money, right? So that is where it all started. So there is a huge history starting from gambling. So go look at what are the other ways in which probability. In fact, all renowned scientists you could think of, mathematicians, would have worked in probability. Okay, all renowned mathematicians. Why? Any reason why? See, in the olden days, who supports science, maths? Who was supporting? Kings, the rulers, right? And the rulers, what is of interest? Gambling is one of the important sport, right? Those days, or important activity, and therefore this is considered, the probability is an area where you would see almost all great mathematicians would have worked. And it is also very interesting because things are uncertain, right? That is where interest comes in, okay. So please go and check what are the other ways. So this is a frequentist approach, and then this is what measurable, but this is limit n tends to infinity is to be kept in mind. It is not just n of a by n, not any n. So if I toss 10 times a coin and you get 8 heads and 2 tails, what is your probability of head? Goes by 0.8 and tail goes by 0.2, but that is not what we are talking in probability, okay. This definition, the catch is it is n tends to infinity. There are other ways obviously to define, you will let us know. So that is the definition of a probability. Okay. So as I said, event is a specific collection of sample points. So now when I calculate, when I say probabilities, I am going to talk about define the experiment, list the sample points, assign probabilities to sample points. That can be not done easily. Okay. This third step is not at all easy. Right? How do I assign probabilities to sample points? In reality, that is not going to be easy. In an ideal situation where you know, like simple cases like throwing a die or a tossing of a coin, you can do it. But if I ask you in a clinical trial, assign probability to each outcome, how do I know it a priori? That is when statistics comes into picture. You understand the difference where stat and probability, when you know things, that is the best, but most often you will not know the probability values. So, and then the other, so we call it as loss of probability, right. So, we have defined what is a probability. Now, we talk about probability rules for sample points. So, what are the rules? The probability of occurrence of any sample point must be between 0 and 1. What does 1 mean? Sure event. What does 0 mean? That is where the catch is. It is a rare event. To give you an irony, okay, do we have a sharp object like a pencil? First, and don't open it, just pass it. So, what is the probability of this hitting a small point there? What is the probability of this pen hitting a small point there? 0. Why is it 0? I am asking what is the probability of this pen hitting a small point there. So, if you assume sample points, if you take points, it will be by definition what? By definition of probability, limit n of a divided by capital N when n tends to infinity. What is n of a here? I am saying some point there. What is the probability? What is the favorable event? I am throwing this thing. So, what is n of a? 1. 1 divided by infinity? But the irony is, I hit only 1 point. So, the outcome has to be what? You see the irony? The outcome you know is, it has to hit only 1 point. Right? You see the interesting fact? The outcome is actually it will hit only 1 point. This can it hit the entire room? If you throw, it will finally hit only 1 point. But what is the probability of this hitting a 1 point? 0. So, that is the irony. Okay, you understand the irony, right? When you start the experiment, its probability is 0, but it can only hit a small point in that. Very interesting. So, how do we define probability in this case? I will not define it as a point. I will say what is the probability that it will hit this region, then the probability will be big. Okay. If I ask for a point, it may be 0, but remember it is an irony because finally something has to happen and it will hit only 1 point. Okay. So, probability 0 indicates a rare event. It does not mean that it will not happen, it is a rare event. Why is it a rare event? I could have thrown anywhere in this room. So, when I begin looking at the entire sample space and this hitting a small point should be very rare, but finally one of the rare events have to happen. After the experiment, one of the rare events will happen. So, it does not mean that the outcome cannot 0 does not mean that it is not, does not occur, it is just a rare event. Okay. Only when you say null, then it means it will not occur. When I say probability is null, then I am very clear that it will not happen. Okay. So, probability null and 0 has a very very distinct phenomenon thing. And the probability of all the sample space must sum to 1, something has to happen. Okay. So, these are the rules of probability. Okay. So as I said, defining the probability, define the experiment, list the sample points, assign probabilities to sample points, which is difficult, collect all sample points in the interest. Sum of the sample point probabilities is the even probability. We know what we are talking about. Let's say if tossing of a coin or throwing a die is the easiest. We know because it's all of them are same to us, 1 to 6. So we say what is the probability, 1 out of 6, and suppose if I say greater than 3, then I know it is 3 out of 6 is the probability of that, even that it is greater than 3. Okay. So if sample of n elements is drawn from a set of n elements, so you are trying, so in this case a pack of cards or whatever, right, you are drawing n elements from a set of capital N elements, then you go by what, permutation or combination? What is this, permutation or combination? Huh? Is it permutation or combination? Combinations. N factorial divided by n factorial into n minus n factorial. Okay. So that is what I said, if a sample of 5 elements is drawn from a set of 20 elements, the number of different samples what you can collect. So this is about number of different samples you can collect is the following. You have so many different ways in which you can take out the sample itself. So that should tell you that statistics, every statistic, is it a random or is it deterministic? Every sample quantity, every quantity that you measure from a sample, is it a deterministic quantity or a random quantity? You understand my question? You take a sample, you derive sample quantities like mean, variance, etc. Is it deterministic or is it random? Why? There are how many ways to take in this simple example? There are at least 15,000 ways in which you could have taken the sample. So do you think all 15,000 will give you the same mean? So that should tell you, even if you collect the same sample size, okay, it does not matter, all of you take 10 samples of some quantity and then 10 temperature measurements using a sensor, none of you will get the same mean, very rare. Okay. So that is why all the statistics, whatever you measure from the sample, are all random quantities, they are all not deterministic. That is why people forgive statisticians even when they say like exit polls, right, same number of samples could have been collected by India today and somebody else, but the results may vary. So now you cannot catch hold of somebody. Why? As a statistician, he did whatever is possible with the data, but remember it has to be taken with a pinch of salt that the statistical parameters or the quantities that you estimate from the sample are random by itself. So x bar, is it the sample mean, is it random or deterministic? X bar is a random variable, random quantity. We formally define what is a random variable, x bar is a random quantity. So when you all know about unions and intersections, right, A union B, A intersection B, okay, I do not need to tell you that. So this is a very simple Venn diagram, okay, unions and intersections. What is independent and what is mutually exclusive? So this is complement, you know what is a complement, right? A complement is what is not in A, okay. So complementary events, we know what is probability of A plus A complement, etc.